Okay, we are going to look at our beams some more. We last time looked at beams and we did shear force, we did bending moment. We did those internal shear force bending moment calculations by slicing the beam open at a particular point. So we could solve a problem that gave us the diagram of a beam, free body diagram, and asked us to calculate a flexural stress at a specific point in the beam. So that is one way to go about doing things. We also might want to solve a problem where we don't know the specific point. Maybe we're given a beam and we want to find the maximum flexural stress anywhere in the beam. So the process that we used last time would be a little bit cumbersome to do that. So what we're going to do today is we're going to create what are called shear and bending diagrams. They're literally pictures of a shear force and a bending moment in a beam. So shear and bending diagrams. Sometimes you'll see these written as V and M. So V is shear force, M is bending moment. They're going to look like this. Let's see if I can find one. They're going to look kind of like this by the time we're done. So you'll have a beam with some kind of loading on it at the top. You'll have a picture that represents the shear force at anywhere in the beam. And underneath that, you'll have a picture that represents the bending moment anywhere in the beam. And so we'll develop a set of rules to construct these things. To do that, we're going to take a generic beam. Just doesn't really matter what this one looks like. What we're going to do with this beam is we're going to put one of each of the loads that we're going to be concerned with. So we're going to put a point load on it, a distributed load on it, and a concentrated moment on it. Here are some reactions. We don't really need those, but for the beam to have a free body diagram that's actually in equilibrium, we'll put them on there. And then I'm going to also draw the moments and the forces and the distributed loads. I'm going to draw them in a different orientation than I normally do. And that's just so that some signs will work out in our equations better later. So I'm actually going to draw the point load going upwards in the positive y direction. We'll put a distributed load on here, also going in the positive direction. We'll call it W. And then we'll put a concentrated moment here going clockwise in the positive direction. So clockwise positive. So this, now I drew an evenly distributed load here. We could have drawn any particular shape, a sine wave or whatever kind of shape that we wanted to do for that. It's not, the shape of it is not important for what we want to do today. So I just drew one that's evenly distributed. What we're going to do is we're going to take a tiny little piece of this beam and analyze just that tiny section. So this little section is going to have a width of delta x. So that we can make it go smaller and smaller and smaller as we need to. So I'm going to take just this little boxed in section. I'm going to draw that bigger, and that's what we'll actually work with. This is just kind of setting up what we're going to work with. So here is a bigger view of the little section that we cut out of this beam. And it has all of these loads. We cut out the point load, P. We cut our distributed load. And we're making them all go in our positive direction. That doesn't affect how we will actually solve things once we develop our rules. It's just so that our equations end up with positive numbers in them, positive variables in them. We also put this moment in here. Now, since I've cut these open, I have to create the internal forces. So remember that we do have a sign convention for if you're looking at this side of a diagram of a beam, we have to draw the shear force and the bending moment in these orientations. And if we're looking at this side, we have to draw them in these orientations. Now, this bending moment is not the same as this one, so I'm going to label this one as the left-hand side, that's an L, and the right-hand side. Same thing with the shear force. They're not necessarily the same. So this will be the one on the left. This will be the one on the right. I think, well, let's label our delta x on here. So this distance is delta x. And we may, as we develop our rules, use that delta x. Okay, so this is a tiny, that we can even make tinier section of a beam that has one of every kind of load that we're going to deal with on it. What we're going to do is this little piece is in equilibrium. That means we can apply equilibrium equations to it. And the first one that we're going to apply is the summation of forces in the y direction must be equal to 0 for this section of the beam to be in equilibrium. So I've got VL, so the shear force on the left-hand side of the beam, it's going upwards, so that's a positive in my equation. Plus P, there's one of the reasons I put this going upwards so that I get a plus in here. Plus, now this is a distributed load, so normally when we're writing equilibrium equations in the x or y direction, then we lump this. So the lumped version of this distributed load would be W times delta x, and it's pointing upwards, so plus W times delta x. VR I've got going down, so minus VR, that's the shear force on the right hand side of the beam. And that's it. All these moments do not create forces in the y direction, so I don't have to deal with those. These have to add to 0 in order for this piece to be in equilibrium and not moving up or down, which I know it's not doing. I'm not counting the fact that, you know, this beam could deflect and like bend this upwards. I mean, this isn't translating up or down, so these forces add to 0. Now this VR, I'm going to rename it. I'm going to leave it the VR, but I'm going to redefine it maybe. So I'm going to say that VR is actually equal to the shear force on the left-hand side plus any amount of change between this point and this point, so plus delta V. And so I'm going to use this definition to put into what I have labeled as the shear on the right-hand side of the beam. And that would make this equation VL plus P plus W times delta X minus this term, VL plus delta V equals 0. And you can see here I've got minus VL plus VL. So those subtract one another. I've got negative delta V, so I'm going to take that negative delta V and move it over to the other side of the equal sign so that it becomes positive delta V equals, and then all that's left over here is P plus W times delta X. So this gives me an equation that describes the change in shear, so delta V, the change in shear, based on point loads and distributed loads. Notice it doesn't have anything to do with the bending moments here. It's just point loads and distributed loads. So I'm going to take this equation and derive some if-then statements. So an algorithm that we can use to draw our shear and bending diagrams. So I'm going to recopy this. Delta V equals P plus W times delta X. All right. We'll come back to that page when we do our moments here in a second. But if, then, and we'll have a couple of rules. So one scenario, if P equals 0 and W equals 0, so this would be a section of the beam where there's no point load and no distributed load. So in our little picture, maybe it's, you know, over here somewhere or over here. There's no point load, there's no distributed load. X is horizontal, axis here. So if these are both 0, then looking at this, it says if that's a 0 and that's a 0, then delta V must equal 0. And so to describe that, it would mean that there is no change. So there's delta V is the change in. So no change in shear for this section. So when we're drawing our shear and bending diagram, there's no change. It's just a constant value. It doesn't mean it's 0. It just means that it's not changing from whatever it currently is when I started drawing that particular line. It stays that value until I get to a point where this is not true. One of these is not true. So let's just say that what if P does remain 0, but now W is not 0? So here I would have P is 0, and I would have delta V equals W times delta X. So the change in shear is equal to basically the area of that distributed load for this section, W times delta X, which was, remember, that was how much distributed load, or the magnitude of the distributed load times how much there is of it. You can also rewrite this delta V over delta X equals W, just moving the delta X over, dividing it through both sides. This term is the slope, dy over dx type of thing. So the slope of the shear diagram equals W. So W is going to be things like 10 pounds per foot. Now, normally it's going to be negative because normally W is, pushing down on the beam, this way. I drew them positive because I wanted the positive signs in this equation that we're developing. But most of the time, W is actually going to be negative 10 pounds per foot or whatever. And this would say that the slope of the shear diagram is that value. So in our example here, that would be, here's the distributed load, and here you've got a negative slope, and it's not constant. There is a change in the shear value here. The slope itself is constant. It's a straight line, but it's the change in shear is equal to W, the distributed load, times how much of the distributed load you have in that section. Okay, and we'll work this thing out step by step in a second. So the other thing that could happen, or another thing that could happen, is P does not equal 0. So now there is some value for P, and remember P is the point load, P. So point loads exist at a point, so we're going to send delta X to 0. So as delta X goes to 0, delta X is over here. So as we narrow in this, we narrow in until we can only see the point where that point load is applied. Then this goes to 0, and delta V equals P. So the change in shear is equal to the magnitude of that point load. So this is a step change. So here with the distributed load, you have a gradual change from one point to another. But with point loads, you have a step change. It just immediately goes down or up, depending on if the point load is, whoops, we're off the screen. If the point load is down, or here's a point load that goes up, the reaction at A goes up. And so this is a step change every time you have a point load. So let's actually start working on this problem now that we have some rules. All right, so I'm going to draw just a line to represent the beam. Let's put it right here. Is that long enough? Let's make it a little longer. There we go. All right, so this is our beam. It doesn't matter as far as when we're drawing the shear and bending diagram if it's an I-beam or a tube or a 2x4. It doesn't really matter. Those cross-sectional properties come in when we try to calculate the flexural stress. But for drawing a shear and bending diagram, the beam itself doesn't actually matter. It matters what's applied to the beam. So let's apply our forces. We're going to put point load. This will be 10. I'm not going to write the units on here, so all the units are in kip and feet, so that we can keep a cleaner diagram over here, because there's going to be a lot of numbers and things on the picture. Let's put a distributed load, and now notice I'm drawing them in their normal orientation where they're pushing down on the beam. Let's put a concentrated moment over here. And then let's have this beam simply supported, so there must have been a reaction at A. And let's put the other support over here. Reaction at B. This distributed load, I'm going to make 2 kips per foot. This concentrated moment, I'm going to make it 3. And then we've got to figure out values for RA and RB. We're going to need to draw reference lines, like these vertical lines here. So I'm just going to take and draw a set of lines all the way down, and then we'll dimension it and work from there. So something like this. Let's put one here where the concentrated moment is going to be. My pen seems to be struggling here a little bit. I think it'll be all right. Let's put one at the beginning of the distributed load. Let's put one for the point load. And then let's put one at the beginning of the beam. So these lines will help us kind of just organize our graph and maybe not forget where we have one of these loads that we have to deal with. All right. Before we get too far, though, we have to have numbers for reaction at A and B. So the only way that I know to do that is to do summation of moments about A, maybe, and that'll calculate B. And we can do forces in the y direction to calculate A. So let's write summation of moments about A equals 0. We need to label our dimensions, though. We can't go too far without dimensions. Let's make this first one 3 feet. Now I may not have drawn everything perfectly to scale. 1 foot. This is another 3. Let's make this 1 and 2. So that gives us 6, 7, 8, 9, 10, just like we want. Total feet. All right. So this is 10 kips times 3 feet. Clockwise, I'm doing moments about A. So 10 times, let's just do it this way, 10 times 3. This is a distributed load, so normally what I've been doing with those is creating a lumped load that I can use temporarily to put into equations like the moment equation or forces in y. This was a 2 that I wrote right on top of, but this is 2 kips per foot over 3 feet, so this is 6 kips, and this distance would be 1.5 feet. So that gives us plus 6 times 3, 4, 5.5. Then we get to the concentrated moment. I've drawn it counterclockwise. I said that clockwise was positive, so this is just minus 3. RB is a counterclockwise moment about point A, so that's also a minus. Minus RB times that whole distance is 3 plus 1 plus 3 plus 1 plus 2 is 10. And those have to add to 0. So when I solve this, I get moving the negative RB times 10 over to the other side. RB times 10 equals 30 plus 6 times 5.5 minus 3 is 60. Therefore, reaction at B, when I divide by 10, is 6. And I'll put the units here just because I don't really like not using the units, but it's just too cluttery to put them on this picture. So 6 kip. And then I can do summation of forces in the y direction equals 0, and I've got RA minus 10 minus 6. This does not create a force in the y direction. Plus RB equals 0. RB is 6, right? So 6 minus 6 just cancels each other out, and therefore reaction at A is equal to, but I move the negative 10 over to the other side, it becomes positive, 10 kips. So there are my two reactions for A and B. So this is normally what you have to do first, is you have to figure out the external reactions from whatever pins and rollers are holding this thing up. So let's write those in. RA was 10 and RB was 6. Now what you do is we're about to draw our shear diagram based on the rules that we just created. So I'm going to create a reference line somewhere in here that will be kind of the 0 line, so the baseline, datum, whatever you want to call it. So there is where V equals 0, and all of these will be in units of kip. And we're going to have to deal with things like 10 and 6. So I'm going to go 2, 4, 6, 8, 10. And then we'll go -2, -4, -6, -8. And those will be in between there. All right. So I've kind of created a little chart that I can plot on here. Maybe let's zoom in over to that section. All right. When you're drawing the shear diagram, let's draw it in purple. You start at 0 and you follow these rules, and basically you're looking for anywhere there's a point load. Here's a point load. Even though it's a reaction, it's still a point load. A point load, a distributed load. We don't care about the concentrated moments in the shear diagram, so I can ignore that. And there's another point load. So the very first thing I see is a positive 10, so it's going upwards, point load. That falls into P does not equal 0, it equals 10. So the change in shear is equal to P, in this case 10 kips, and it's a step change. So I go from this point up to 10, and I end up with, a step change. And then from this point, I'm working my way from the left side of the beam over to the right side of the beam. So from here to here, there are no forces of any kind, no external forces. There's internal, bending moments and shear forces and that sort of thing, but there's no external forces between here and here. So when there are no external forces of any kind, I'm in this, there's no point load, no distributed load, there's no change in shear. So that means that the shear doesn't go down to 0, it means it doesn't change. So it stays at 10 kips until I get to something that's going to cause it to change. So there's a 10. And it happens to be that it encounters a negative, pointing down, negative 10 kip point load. So I'm at positive 10. I go down by 10, so I go to 0. And then from this point to the beginning of the distributed load, there are no forces. So I maintain that 0, no change, until I encounter the distributed load. Now it's important that you not worry with this lumped load. I only use that lumped load, the 6 here, when I was calculating the summation of forces in Y, or this moment, summation of moments, but it's not an actual external load. The actual external load is the distributed load. So the distributed loads give me this set of rules. When there is a distributed load, it's not equal to 0, then the change in shear, so the total change from one end of this section to wherever I end this section, in this case the section will end at the end of the distributed load, then that total change will be W. In my case, W is 2 kips per foot, times delta X, which is 3 feet. So the total change from one end to the other will be 6, and it's negative because the distributed load is pointing downward. So it'll be negative 6 kips. The slope of the shear diagram in this section is equal to W. So W, it's right here, is actually a negative 2 kips per foot. So I started at 0. From this point to this point, I'm going to decrease by 6. So I'll go down to, here, negative 6. And the connection between here is a straight line, because it is the slope of this line is determined by what's going on in your distributed load. So if I have a constant distributed load, it doesn't increase, it's not going up, it's not making some curve or whatever, then it's a constantly evenly distributed load. Then I have a constant slope here. So I draw a straight line between those points. And I know to go down by 6, not go down to 6. In this case, it goes down to 6 because I started at 0. But I know from this point to this point, the height here would be negative 6, because the total area under this distributed load is 6 kips. It's 2 kips per foot spanning 3 feet, which is 6 kips. From this point to here, there are no external loads, so I stay horizontal. This line is reminding me about the concentrated moment, which doesn't affect the shear diagram, so I kind of ignore that and maintain horizontal until I get to this point, in which case I see RB, which is pointing up 6. So I go from negative 6 up 6, I go to 0. And this is what should happen. It may not end up perfectly like this one, where you get to exactly 0, because you might have some rounding errors. But this is a picture of the shear force at any point in this beam under this loading condition. And we don't use it very often as far as, modes of failure. Normally the shear force is not going to be the way that these things fail. But we need this diagram in order to construct our bending moment diagram. So it does tell us that the worst case for direct shear failure would be in this first 3 feet, because that's where I have the largest shear force. I have 10 kips from anywhere from here to here. There are 10 kips of direct shear, this guy, in that part of the beam. On the other part, on the very other end, there's 6 kips, so almost as bad, but not as bad. All right, now we need to go back to deriving our equations over here. So to get to these, where do we put them? To get to these rules, we wrote this equation. Now, and we drew this shear diagram. Now we want to draw the bending diagram down here. So we're going to take our same free body diagram that we had, and we're going to write the summation of moments about this center point, we'll call it C, for this diagram. So there's several that are just moments on here, right? ML, MR. We're going to do a similar thing where MR equals the moment on the left-hand side plus the change in moment, however much that equals. is when we get to that. And then we've got M, the concentrated moment. So let's write all of those, and they're just either plus or minus. So this one is plus because I say clockwise is positive. ML minus MR, but MR is actually this term. Plus M. P does not create a moment about point C. It has a line of action that actually goes through point C. The distributed load, now you can look at it a couple of ways. The way I've drawn it here is that it's evenly distributed, and you could break it into two halves. You know, this half with a lumped load there, and this half with a lumped load here. And those two you could look at and say, well, they just cancel each other out. This one creates a clockwise moment that's W times whatever that distance is, and this one creates a counterclockwise moment that's equal to that, and they cancel out. But you don't always have evenly distributed loads on here. There might be some function multiplied times that distributed load that creates a totally different shape, you know, a polynomial or a exponential or whatever shape you have in here. Regardless, we are going to do a similar thing that we did here, where as delta x goes to 0, so this is could be some function of x, and as I make delta x go to 0, then it essentially wipes out the distributed load. So I'm not even going to include it in my equation here. You could write a of x times w and then, you know, half it up or whatever and figure out what moment it creates. I'm not even going to bother with that because I've got a function of x multiplied times whatever moment arm I end up with, which is x, and then I'm going to send, which is a fraction of delta x, and I'm going to send delta x to 0, so it's going to accelerate to 0 faster than anything else in my equation, so I'm not even going to write it down. I do have to deal with these shear forces, though. So how I'm going to do this is they're both clockwise, right? VL goes around C clockwise, and VR goes around C clockwise. So here's what I'm going to do. Plus VL times, and this moment arm would only be half of delta x, right? So delta x over 2 plus, and I'm going to write VR. I'm not going to write all this stuff. VR times delta x over 2. All of this has to add to 0. Let's start narrowing this equation down. Here's my ML minus ML, so those cancel out. My delta M has a negative sign in front of it, so I'm going to move delta M to the other side of the equation to become positive delta M. Equals M. And then this term. So I have a delta x over 2. I'm going to collect that. So plus VL plus VR times delta x over 2. And then I'm going to look at this and I'm going to write it a little bit different. VL plus VR. I'm going to put the over 2 in here and leave the delta x over here. And now what I've got here is I've taken whatever the shear force on the left hand side is, I've added it to the shear force on the right hand side, and I've divided by 2. So all that is I'm taking the average shear in this section. So I'm just going to replace this thing. I could replace it with a term like V average if I wanted to, but I'm just going to use V as the average shear force in this little tiny delta x section, and then I multiply it times delta x. And I get a very similar equation to what I had over here, but now it's describing the moment diagram. All right, let's develop our rules for that. Got to get our shear and bending diagram out of the way. We'll come back to that though, because we still need to draw our bending moment diagram. So here's our equation we just came up with. Delta M equals M, the concentrated moment, plus V times delta X. And we're going to write our if then equations based on that. All right, so we would have basically two scenarios. Well, one where they're both 0 and there's no change in moment, so that's possible. If M is 0, we can write that one down. M equals 0 and V equals 0, then there's no change in shear. No change in shear. There's no change in bending moment. This is not as common. Although we do have that section here. There's no concentrated moment written right here, and there's no shear force. Its shear force is 0. So we do have that section in our free body diagram. Actually, this was ours. That was my notes over there. So it's this section right here. So we do have that kind of scenario going on here. And it just says that the shear force, or if the shear force is 0 and there's no external, these are talking about external loads here. Well, external here and internal here. So if the internal shear is 0 and the external concentrated moments are 0, then the moment diagram just remains horizontal at that point. So that's possible that it happens. What if M equals 0, but the shear force, the internal shear force, is not 0? So this is most of the time, right? So we only have one spot on this beam where there's an external bending moment M, but there's lots of spots where the shear force is not 0, all of this and all of this. So this is most of the case. So if this is true, if M is 0, then I get the equation delta M equals V, that internal shear force, times delta X. So the change in shear is equal to V times delta X. V, or V is the height, V times delta X, that's the area of all of these shapes. So this is the area. In fact, you could integrate both sides. You could integrate here, and you'd have the bending moment equals the area under the shear curve. So M equals area under V shear curve. In fact, usually what I do when I'm over here is I calculate all of these areas. So this has a height of 10, a base of 3, so that's 30. This one has 0. It's unusual, but it does happen sometimes. This one has a height of -6, a base of 3, but it's a triangle. So that is 9, -9. That's just a triangle. This might be one big rectangle, except that I have to divide it into 2. That's why I drew this line, because I do have a concentrated moment in the middle of this rectangle. So this rectangle has a height of -6, a base of 1. So it has -6 area. Then I would take care of the concentrated moment. Then this rectangle has a -6 height, base of 12, or base of 2, which is an area of -12. So there, with those written out, I have integrated the area under the curve there. I can also write this delta M over delta X equals V. So this tells me about the slope, dy over dx, the slope of the bending moment diagram. Equals V, the internal shear force at that point. Now there's lots of different things that might happen here. So I'm gonna, there's 1, 2, 3, 4, 5, 6, 7 different cases, I guess. So let's describe them all. 1, 2, 3, 4, 5, 6, 7. All right, these are my shear force equals 0 lines. So all of these are, you know, the little line across here. And I could have, I did them in purple, so I could have a shear force that's above the line, so a positive shear, like this section. And if I do, then the bending moment, so this is the shear diagram over here. And the bending moment diagram, I'll show what shape it will take in this column. So it would be, this is a constant shear, so that means I have a constant slope, so a straight line, and it's positive because it's above zero, so it's upward. So it does something like that. I could have constant shear but negative, so that would be a straight line but going down. I could have zero shear, so I'd have zero slope, which is horizontal. Then I could have stuff like this, where there's not a constant shear over a region, but there's a changing shear, and there's 4 of those that I could have under an evenly distributed load. Now actually, you know, this distributed load could be any shape, which would change this shape. For our course, we're only going to deal with evenly distributed loads just to narrow down the things we're going to have to deal with. So we could have one where it's positive, so it's above zero, and it's getting more positive, larger numbers. So that means the general slope is, let's see how I might want to do this. The general slope is upwards, but the slope at any point is getting steeper and steeper. So it's going to do something like that. I could have a similar one where it's positive, it's above zero, so the general slope is still upwards, but at any point I'm losing. It doesn't have to go all the way down to zero, but this shear force is a larger number than wherever this one is. So the shear is making a more shallow slope here, but it's still positive. So it's going to do something like that. If it gets to zero, then it will actually level off horizontal. And then I could have the 2 negative ones, like this. So both of these are below the axis, so they both have generally negative slopes. This one is getting more negative, so that means it's getting more steep. This one is getting less negative. In fact, I drew it going to zero, which would make it horizontal, like that. So these are all of the possibilities for how we might have to interpret the shear diagram and the corresponding slope that goes with the moment diagram. Obviously, we are limiting ourselves to just evenly distributed loads. If you have other shapes here, then this shape will be you know, some other more convoluted, you know, more curved shape or whatever, which will give a higher order curve in the moment diagram. But we're just not going to deal with those in our case. One other thing could happen. I'll write it over here. One other rule I don't have room for in my column, so we'll make a new column. What if m does not equal 0? So if m does not equal 0, as delta x approaches 0, so as I narrow in, where's my picture? As I narrow in to just the point where that concentrated moment exists, then I've essentially eliminated this term. Delta x is going to 0, and delta m equals m. So that says that there's a step change in the moment diagram, just like the point load, just like this when p does not equal 0. So there's a step change in bending moment diagram. All right, so let's try to use these rules and draw our bending moment diagram for the beam that we're working on. So we've already drawn the shear diagram, which we need. Most of the bending moment diagram comes from integrating the shear diagram. And we integrated it by calculating the area under the curve, and we broke it into individual little shapes, calculated those areas, and now we've got the area under the curve. We need a horizontal line. Let's see if I can find my ruler. Well, just use this. I don't know where I put it. Somewhere down here. This will be our m equals 0. Our units are kip feet. And we're going to have to go up to, there's a 30, so we're going to have to go up to 30 or so. So let's make 30 somewhere up here. So if that's 30, then, there's 15 and so forth. Here's negative 15 if we need it. Something like that. We don't have to be super accurate, but the more correctly you draw this, then the better it's going to convey the information that it's trying to convey. All right, we start at 0, and we have an area in our shear diagram that is a constant shear. From here to here is a constant shear. That means we have a constant slope, and the total change from this point to here is the area under that shear diagram, which is 30. So we're going to go up to here. Found my ruler. So we're going to go from 0 to, I usually like to write these numbers on here, 30. And it's a straight line. So that was the one where we wrote this guy. We had a positive constant shear, so we have a straight positive slope in our moment diagram, like that. This is the unusual section where we actually have no shear, no concentrated moments. So in this little section, there's no change in bending moment. So it's just horizontal. That was, this one. It's just horizontal. It's not common because most of the time your beams don't have sections with 0 shear in them. I've arranged this one so that it did, but they don't always, or they don't often even do that. All right. Now we've got a section where there is negative, so we're going to have a downward trend, but it's not a constant shear. It's getting more and more negative. So that is this scenario where it's negative and getting increasingly negative. So the curve is going to look this shape. So we actually started at 0, which means it starts out at horizontal, and then we're going to lose a total of 9. So this area is negative 9. It has a height of negative 6, a base of 3. It's a triangle, so you divide by 2, gives you a negative 9. So it's kind of handy to keep a running total in your calculator. You start at 0, we added 30, we added 0. Now we're going to subtract off 9, and we're down to 21. So 21 is, I don't know, somewhere in here. Something like that. And it curves. It starts out horizontal and then has a curvature to it that matches that curvature. Then I'm back to an area that has a constant negative 6. So I'm going to have a constant slope here. It also has an area of negative 6. So the slope is related to this 6. The height, or the negative height of the section here. This is the area because it has a base of 1. So negative 6 times 1 is also negative 6. So I'm at 21, subtract off 6, and I go down to 15, which is right here. So, and it's a straight line because this is a constant value for shear. So it's a constant slope here. And it's negative because it's a negative 6 on the value for shear. This line is reminding me that, oh yeah, you've got a counterclockwise 3 kip foot concentrated moment here. So when I have a moment that's not 0, then I have a step change. Here, this we have to relate back to this sign convention here. And if an external concentrated moment is counterclockwise, those are going to give you negative step changes in your bending moment diagram by our sign convention, so that all of our bending moment diagrams look the same. You could do everything backwards, you know. You could put these opposite of what we've drawn, and you could say that counterclockwise is positive, but our convention that we're using is that external moments, concentrated moments on a beam, when we're drawing a shear and bending diagram, if they're counterclockwise, it's going to give us minus, in this case, 3. So minus 3. Brings us down to 12, which, I don't know, is somewhere in there. And it's a step change, so it goes straight down. And then the last section is a constant shear. It has a total change of negative 12. I'm at positive 12, so I actually go to 0 exactly. That doesn't always happen. This one is, you know, contrived in a way to where it works out perfect. But a lot of times you'll get here and you'll be off by a couple of tenths or whatever. Depends on the scale of these numbers. But it's okay if you've rounded and didn't get exactly to 0, but you should be near 0. And this is a constant slope because it's a constant shear. And now we have an entire picture of the bending moment diagram anywhere in this beam. So if you wanted to, you could shade it in. I don't know if I really need to do all of that, but I guess I've started it now, so I'll finish it. They're getting further apart. All right, so we can also see that this little section right here has our maximum bending moment. Normally it's a peak. In this case, there's an entire section of the beam that has the maximum bending moment of 30 kip feet. And we could take that if we were interested in doing that. It's not part of what we're doing right at this moment. But we could take that M max into sigma equals negative M times Y over I. And we could put a maximum value now. And we know that it's somewhere between these 2 points on our beam. That it's most likely to fail by flexural stress. At least that's where we're going to have our highest bending moment, which usually corresponds to our highest flexural stress. Okay, so that is the process for drawing a shear and bending diagram. It took us, you know, nearly an hour to do that, but we also, you know, derived all of our rules that we were using to solve for, you know, how we're going to draw these shear diagrams and how we're going to draw the bending diagrams. Once you've kind of committed these to memory, I don't know if you need to necessarily commit this picture to memory or not, but the idea of this picture you need to have in your memory. Then drawing one of these doesn't take long at all. You draw your free body diagram of your beam, you find your external reactions, and then you start drawing the shear diagram. You integrate the area here of the shear diagram, so you basically just calculate all of the areas of the individual triangles and rectangles that you have in the shear diagram. Then you use that to construct your bending moment diagram. Remembering to include any concentrated moments. It's easy to forget one of those. That's why I always draw the line here that reminds me of what to do, not to forget that I've put a concentrated moment up there. Okay, so next time, Monday, we'll do some more of this. There's a couple of other little details that we'll need to go over. There are no changes. This is all correct, but there's some like special cases you might run into that we'll have to show you how to deal with those in case those happen. Like for instance, if you have one of these changing, you know, a distributed load here, a changing shear force that goes across the 0 line, how do you divide it up into some of it's positive and some of it's negative? So we'll have to see how to do that. It's not too complicated, and you probably can figure it out on your own, but on Monday we'll go through that, and we'll keep adding on to this. Also, if you take this picture, the bending moment diagram, and kind of imagine it flipped upside down, sort of like this, but really, you know, like flipped over, mirrored down here. That is sort of, you know, minus the fact that it's got straight and sharp corners and a step change over here, but that shape is similar to what you would expect this beam to bend in if you mirrored this upside down. It would look something like that. It wouldn't look exactly because of the straight lines and the gaps over here or whatever, but it would look similar. So you can kind of get an idea of the beam deflection based on the bending moment diagram. We were actually getting ready to plot the beam deflection, not based off of this picture, but based off of the loads and the shear forces and bending moment in the beam. We'll be able to plot and derive some equations that will show us the deflected shape of the beam. And that'll be soon, next week. All right. Until then, if you have any questions, let me know. Write them in the comments here, send me an email, whatever, and we'll try and answer any questions that you can come up with. And we will do some more bending moment shear diagram from scratch. A lot of the problems we start from now on for this section, the second third of the course, will involve these shear and bending diagrams. You really do need to get a handle on how to draw these accurately. So we'll see you on Monday, and let me know if you have any questions.